Hi, everyone. My name is Quentin Baghi. I'm working on Lisa data analysis, but today I will do an introductory talk on signal processing. So for many of you, it must be basic concepts that you already know, but we decided to do this introduction on the concept of signal processing to have everyone on the same page for the workshop. So in my talk, I will talk about the Fourier transform and the special artifacts that you get when you deal with finite time observations and discretized time series. Then I talk about the noise as well, what the assumptions that we can do about the noise and the definition of the power spectral density that Viola already told you about. And then if time permits, I will do some overview of time frequency analysis. Okay, so the Fourier transform, why will I talk about this? So in gravitational wave detector data analysis, you have observables that are usually time series, so continuous functions of times, at least the observables, they are continuous function of time. For example, the deformation of this matrix as a function of time can be described by the function, which is deterministic, let's say. But also, of course, you have also many perturbations in your measurement, which can be thought of as a realization of stochastic processes. And these are described by distributions, right? So they are random in nature, they are described by distributions, whereas when I talk about deterministic signals, it's more like described by functions. However, it's not super convenient to work in the time domain because it can be computationally expensive, and also the noise statistics are hard to represent. I will talk about that. So we often use another representation to describe these data, which is called the Fourier transform. So this is this integral transform coming from, that takes a time domain function and it converts it to another function of the frequency. And this is given here. So why do we do that? There are at least three reasons we can think of. First, it's really to understand what is the frequency content of the signal. It also can be useful to have a sparse representation of the signal, which is quite compact if the signal has a short bandwidth. And also, the noise statistics is actually has nice properties and is quite compact as well in this representation. So that's why we use it. So as you may know, if S of f is an integrable function, then there is the reverse operation. It is called the inverse Fourier transform that I gave here in this equation. Okay. So some interesting properties that you may also know, but I kind of review them here. The Fourier transform is linear. When you have a shifted function in time, then it converts into a product with a complex exponential phase like this. So S of t minus t0 becomes, this exponential minus 2i pi f t0 times the original Fourier transform, sorry. Then an important also property is time contraction. Right? If you squeeze the function in time, then it stretches in frequency. So it's kind of an important property that we will see. Conjugation, if you take the Fourier transform of the complex conjugate of the initial function, then you can cover it by taking the complex conjugate of the Fourier transform evaluated at the minus frequency. And so that's why that for real valued functions, you have that the Fourier transform of the negative frequency is equal to the complex conjugate of the Fourier transform of the positive frequency. Derivatives as well. If you take the Fourier transform of a derivative, then it converts into a multiplication of 2i pi f times the Fourier transform of the original function. This is quite convenient, especially when you want to solve for differential equations. Another thing I wanted to remind or state is that if you have the convolution of two functions in time, like here I convolve S with G, then the Fourier transform of this convolution gives you the product of the Fourier transform of the two signals. So this is an interesting property. And another property that you may know is the Parseval theorem, which conserves the inner product. So you have this integral of S of t times the complex conjugate of G, which is conserved, and you have the same for the frequency domain. And if you take S equals to G, then you end up with the conservation of power, right? Because this integral of the square modulus of S will be equal to the integral of the square modulus of S of F. Okay, so with that in mind, I will carry on and talk about another property, which is the uncertainty principle, which means that basically if you have a function that is widespread in time, it will be concentrated in frequency and vice versa. So let's take some kind of measure of a zero mean signal spread in time first. So if you define it in time, okay, you can define a bit like the standard deviation. You can define this quantity here, which is normalized by the energy of the signal. And you can do the same in the frequency domain, like define a measurement or measure of the spread in frequency. And you have this relationship here. So here, E, as I said, is the total power. You have the fact that sigma t times sigma f cannot be smaller than 1/4 pi. So actually, you cannot have both, an infinitely tiny or peaking function in time and an infinitely peaking function in frequency simultaneously. That's not possible. So in practice, of course, we are coping with fundamental limitations. Sorry. We see the universe through a window. We don't have the eternity to observe it. So this is the finite time problem, let's say. And another thing is that when we acquire data, when we record data, they are discretized. So they are usually evenly sampled in time. And so these are consequences when we do Fourier transforms. And I will talk first about the first of these two issues, let's say, which is finite time window or windowing. So let's say we observe a certain duration t of a signal, right? And this results actually in a smearing of the frequency content of the signal. Why? Because this is like we apply product in the time domain, right? We multiply S by omega of t, where omega of t is a window in time, which has a duration t. And we know that the Fourier transform of a product is a convolution. And so you see that now the Fourier transform of t will be the convolution of the initial signal with the Fourier transform of the window. So to illustrate this process, we usually take a signal which is a continuous wave, a sinusoidal signal with frequency f0 here. This is what I illustrated here. And if we observe it during an infinite observation time, you know that, well, its Fourier transform is a sum of delta Dirac function that peaks at f0 and minus f0, okay? So here I just represented the positive frequencies for clarity, but you have the same for negative frequencies. And you have this, okay. If now you observe this signal during a finite observation time, you have this convolution effect that I was telling you about, which smears these sharp peaks like this, and you obtain this cardinal sine function, which is the Fourier transform of this window shifted at the frequency of the signal. And so this is the blue curve that I represented here, and the width of this curve depends on 1 over the observation times. Okay, so the larger the observation time, the shorter this width. And actually, I wanted to, well, illustrate that, right? If you increase the observation time, you decrease the width of the signal, and you also, of course, you also increase the amplitude of the signal. So you have actually all these, secondary lobes or side lobes here that will contribute to the smearing of the signal when you convolve it with the Fourier transform of the window. Okay. Now, a second issue, let's say that when we cope with real data, is discretization, right? So what happens when we have evenly sampled data stream? Let's consider a signal of time, S of t, and we assume that it's sampled every delta t, okay? So we take data every delta t, and you end up with this representation, let's say. And it's like you were multiplying in time your original signal as of t by a direct comb, which is composed of a series of delta functions that are picking every delta t. And if we take the Fourier transform of this, well, it will do convolution with the delta direct function, and you will get basically an infinite series of S of evaluated at delta t times n times this exponential to I pi f and delta t. And so when you do that, what you obtain is actually a continuous function of frequency. So it's a function of frequency here, which is continuous, and its periodic function with the periodicity equals to the sampling frequency, Fs, okay? So you get a replication of the Fourier domain transform, or of the Fourier transform, every Fs. And this means that when you discretize your function in a domain, then when you take the transform, you get a periodization of the transform here. And actually, the reverse is true as well. Okay. So we get a replication, and actually this allows us to speak about the Nyquist-Shannon theorem, because let's say that you have a signal that has a maximum frequency b. So in our case here, you have a bandwidth where the frequency goes from minus b to b. This is so b is the maximum frequency, and you see that if this sampling frequency is too small, then the replication of the Fourier transform, the periodicity of the Fourier transform will go into this band, and so you will have what we call aliasing, right? And that's why the Nyquist-Shannon theorem says that B should be smaller than Fs over 2, so which is called the Nyquist frequency, because you really don't want to have this replicated into the band. Okay, so I talk about discretization. I also talk about windowing. And so let's bring windowing into play along with discretization, so both at the same time. So here we go back in time domain. We sample our signal every delta t, but this time we observe it only during a duration t. And this is what is mathematically written here by a multiplication of the data by a window, wt, right? So you have, the effect of the window, you have the effect of the direct comb that we saw, and you have your continuous signal here. So if you take the Fourier transform of this, you get this now finite series, with n, being the size of the time series that corresponds to the observation time. And this is still a continuous function of frequency, which is periodic. And then, since we're working with computers and we need to record samples of the frequency domain data, and so we will have to sample the Fourier transform itself, right? So now we're working in the frequency domain, and we are sampling the Fourier transform every delta f, let's say. So that means that we multiply the spectrum with a delta Dirac function that picks every delta f. Okay, so delta f is this separation here that I wrote here. Okay, between two points, and so we have to choose delta f carefully, in the sense that we know that some discretization in one domain yields periodization in another. So that means that if we discretize the frequency domain data, then we will get a periodic function in time of period 1 over delta f, right? And so this period 1 over delta f should be larger than the observation time of the window. Otherwise, you will get also replicated features inside the time domain. So that's why it will be wise to retain frequency samples that are spaced by 1 over t, where t is the observation time, or lower, to recover a consistent signal in time and to avoid periodicities, that are smaller than t. So now that we have set the sampling in the frequency domain, we can record it, but in cleverly, because here you have a periodicity in frequency domain, so you have redundant information. So what you can do is also just select samples that are only on one period of the Fourier transform, the discrete time Fourier transform, which is Fs, okay, or period Fs. And so you can store only this one period, and you get this transformation here, which is what we call the discrete Fourier transform. This is what you will use in the remainder of the workshop, right? So it's this discrete sum here. We put a delta t here because we want to have the same dimension as the Fourier transform. And this transform can be efficiently computed through an algorithm called the fast Fourier transform. And you have a reconstruction formula here, which takes the discrete Fourier transform to go back in time. Okay, so now that I introduced the Fourier transform and the discretization issues and the finite time issues, let's say, I will talk about noise statistics, and in particular, how to represent noise statistics in frequency. So, as we were saying, data can be composed of deterministic signals and stochastic processes. So you can think of S of t as a compact binary coalescence signal, and N of t as some measurement error or some random noise coming from the detector. And we usually describe these N of t as a family of random processes that we call stochastic process. Oh, sorry, a family of random variables. Sorry, that we call a stochastic process. And this is a family N of t of random variables that is indexed by t, which belongs to some index set. But in gravitational wave data analysis, you will assume that these are evenly sampled times. And so you describe this quantity with a cumulative probability distribution, right? It's not a deterministic function. You describe it with this function, which gives you the probability of N of t having a value less than A. So in practice, we are interested in certain moment of this distribution, not really the distribution itself, at least to quantify this power spectral density that we were talking about. For example, the mean that is defined like this, right? Also noted with brackets, and the variance. Okay, these are two moments, the first moment and the second moment of the distribution. And we usually deal also with a collection of values, right? We saw that we had this time series. And for example, let's imagine that we are dealing with a vector of size n, which is a collection of evenly sampled n of t. One particular stochastic process I wanted to introduce is the Gaussian process, which is actually useful because in nature, I mean, you know, the central limit theorem says that if you have a lot of independently distributed random variables, if you add them together, then the distribution that you get is close to Gaussian. So that's why there are a lot of, you know, instrumental noises, for example, or processes in nature that are nearly Gaussian. And this is described by this probability density here, which is the derivative of the cumulative probability density. And so I recall it here. And it's mainly, you know, it's only described by two parameters, the mean, which is a vector, and the covariance, that is a matrix. And the covariance is described by what we call the covariance operator, which is basically given by the covariance of any two samples at different times at t and s, okay? And so this populates the covariance matrix entries, which are given by this covariance operator. So the Gaussian process, you know, without any assumption is not very useful to describe data because it has a lot of, you know, this covariance matrix has n by n elements, the mean as well. So the mean has n elements. So it's useful to do some approximations, and one major approximation is the stationarity assumption. So basically, we say that statistical properties of your stochastic process do not change with time. So Viola talked about it a little. And there are two, let's say, levels of this assumption that you can make. The first one is strict sense stationarity. That means that, you know, if you take this collection of vectors, so this vector, this correlation of measurements here, and you shift it by a time tau, then the shifted version has the same probability distribution function. Okay, it doesn't change. So this is strict sense stationarity. Another less strong assumption that you can make is wide sense or weak stationarity, where you say that only the first and second moments are invariant by time shift. You know? So that means in practice that the mean and variance of your stochastic process are independent of time. And the covariance operator depends only on the time difference. Why? Is because if you have an invariance in time shifts, then k of ts is equal to k of t plus tau and s plus tau. And if you take tau to be equal to minus s, then you end up with k of t minus s and 0. So that means that you only depend on the time difference. And that's why you can define a simpler function that is called the autocovariance function that just gives you the covariance between one data at time t plus tau and the data at t. So with 2 points that are separated by tau. So this is the stationary assumption. And actually for Gaussian processes, these two assumptions, strict sense and wide sense, they are the same because the Gaussian distribution is only described by mean and variance. So that's now bring us to the power spectral density. We can actually represent this autocovariance function in frequency. And if we take the discrete time Fourier transform of the autocovariance, we obtain the power spectral density. And actually you can get the autocovariance function from the power spectral density as well. And so this power spectral density function, you can think of as S of f times df gives you the average contributions over many realizations of the process to the power of the stochastic process coming from a small region in frequency, okay, between f and f plus df. And this completely characterizes the covariance of a wide sense stationary process. And it has units of amplitude squared divided by Hertz, okay? And so in gravitational wave data analysis, pay attention that we usually use or adopt the one-sided power spectral density, which is equal to 2 times the power spectral density. It's just because we want to define it only for positive frequencies. So for example, here you can integrate over positive frequencies only. And this is actually what is represented on these plots that Viola showed actually. And here, actually, it's the square root of the power spectral density of the one-sided power spectral density, also called amplitude power spectral density. So this is, a sketchy LIGO noise model. So this is not, this is a toy model. So you will see Francesco's talk with more details about that. Here, it's just for the purpose of the illustration. So the covariance matrix for this White-Sense stationary process has constant diagonal, because we said that it only depends on the difference between the times of the 2 points. Okay, so this is called Toplitz's structure for a matrix. And let's see now if we can derive properties for the covariance matrix of the Fourier transform, or rather the discrete Fourier transform of n. So here I just wrote down the discrete Fourier transform of this noise, okay? And we can show that the covariance matrix of any frequency or discrete frequency k and l is given by this integral here, which involves actually the Fourier transform of the window, which is taken centered at the frequency fk and another at the frequency fl, and the power spectral density as n of f, okay, the one-sided power spectral density. So here you have, let's say, 2 effects that are encompassed by this equation. If you take diagonal only, k equals L, then you see that you have a convolution with the square modulus of the window Fourier transform. And this leads to leakage, this smearing effect that we talked about previously when you have finite observations. And the second thing, if k is different than L, is that adjacent frequency bins are correlated depending on the window. So that means that you don't have a diagonal covariance matrix, at least in general. But fortunately, because otherwise the frequency domain would be less interesting, it is approximately diagonal. So if you take long enough time series, then the covariance of any discrete frequency k and l converge to a diagonal matrix where the diagonal elements are proportional to the power spectral density. So that's why actually this is a very convenient domain, is because the noise representation is very sparse. So we've seen that the covariance of the DFT is diagonal is a large sample limit, and its diagonal elements are proportional to the power spectral density. And I also wanted to say that we have, if we take a zero mean Gaussian process, that the real and imaginary parts of the discrete Fourier transform, so normalized by the square root of 2 divided by t, are normal variables or Gaussian variables with a sigma or a variance that is given by 1/2 of S, where S is the one-sided power spectral density, right? So the power is distributed between the two. So this is for frequency that is different than 0 and then the Nyquist frequency. And so if you take the square modulus of the discrete Fourier transform, then it will be distributed like a chi-square distribution with 2 degrees of freedom, and with 1 degree of freedom for 0 and Nyquist frequency. I wanted also to introduce an alternative definition of the power spectral density that relates to this asymptotic relation, which is that you can also think of the power spectral density as the limit when you have an infinite time series of the statistical mean of the mean of the modulus square of the discrete Fourier transform. So you take many realizations and the infinite time series and the modulus of the square Fourier transform is giving you the power spectral density. So actually, you can estimate this PSD. So let's see how. We can define for any time series D an estimator, which is called the periodogram, right? This is 2 over t times the square modulus of the discrete Fourier transform. So we know that because of leakage, this is not an exact estimator, let's say, of the PSD. It has some bias, which is due to leakage. It's only approximate. So if you take many realization of the noise, it's only approximately equal to the power spectral density. But you have a convolution with the window, right? So if you want to avoid this effect when you estimate the power spectral density, then you need to use smooth windows in time. So for example, that goes smoothly to 0 at the edges. And you take this discrete Fourier transform, including the window here. And if you calculate the periodogram, then you count for the effect of the window by normalizing by the sum of the window squared, to take into account the loss of power due to the window. And you get the window periodogram, let's say. Another problem of issue, let's say, of this estimator, the periodogram, is that it has a large variance, right? Actually, the variance of the periodogram is equal or proportional to the square of the power spectral density. So if you want to decrease this variance, you need to average over many data segments, either in time or in frequency. Usually, I think in the workshop, we do time averaging, which is called the Welsh periodogram. That means that you take several periodograms, possibly over segments that are overlapping in time, and you average them. And then the variance will decrease, inversely proportionally to m. So this is the Welsh periodogram. So we have, decreased the bias due to leakage thanks to windowing, and we have decreased the variance thanks to averaging. So here I wanted to illustrate a bit these effects. This is an example of just a simple periodogram estimates with a rectangular window and single segments. So you see here on the left-hand side, this is the square of the periodogram, and you have the leakage effect that is really significant, right? And this is due to the fact that the rectangular window Fourier transform has these side lobes that are quite important relative to the main one, and they contribute to frequency leakage. So you have, power in high power regions of the spectrum that leaks towards low power region of the spectrum. So if you want to mitigate this, you apply a smooth window and you get this. So this is with a so-called Blackman window. And you see that now the periodogram in blue is following the orange curve, which is the theoretical power spectral density, the one-sided power spectral density. And indeed, you see that these secondary lobes are reduced for the Blackman window because it's smoother at the edges. And this is at the cost of a slightly larger main lobe here. So this means that when you decrease leakage, we usually increase a little bit the correlations between the different frequency bands. Now that we have applied windowing, we can average over time segments to decrease the variance, and that's what we do here. This is a simulation, right? We have average over a few segments, and you see that the variance of the periodogram is decreased. So here you have, let's say, for the same data, you have a trade-off between, increasing the segment size will improve, let's say, the resolution. You will go lower in frequency, but at the same time, you will have more variance. So it's a kind of a trade-off. Okay. I also wanted to show what happens if you inject a signal in this kind of power spectral density representations here, where I have just injected a signal of f naught, of frequency f naught here, and so you see a peak over a certain time, 32 seconds of observation time. And if you increase the observation time, then the level of the power spectral density should remain the same, right? But the amplitude of the signal, since the continuous signal, should increase. Okay, so this the particularity of this representation in density. One thing, now that we have defined the power spectral density, which represents the variance of the signal in frequency, then we can do what we call widening, and this is something that you will see during during the workshop. Is you can normalize the frequency domain data by the square root of the power spectral density and 2 delta f here, and actually all the variance of all the points in frequency domain will be the same. So it's kind of normalization or data conditioning that the machine learning people would say. Actually, you have to be careful. Sometimes if you're applying windowing, then you need to rescale the power spectral, the discrete Fourier transform, which is widened by this to obtain the perfect, let's say, rescaling. Another operation that you can do is band pass the frequency domain data by applying now window in frequency. And it's usually useful when you want to focus on limited frequencies, bandwidth in the frequency domain, and you want also to avoid the low sensitivity of low frequencies and high frequencies. And so you can multiply this data by a smooth window in frequency this time. So this gives you the right-hand side plot. And once you have done that, you can go back to the time domain by an inverse discrete Fourier transform, and you get some normalized time series that actually sometimes will make you visualize a signal that will show up against the noise. So here there is no signal in this simulation. And as a side note, this is equivalent to applying an infinite response filter to the time domain data. Okay, I have 3 minutes left, or something like this. So I will briefly talk about time frequency analysis because this is something also that you will play with in the tutorials. So the discrete Fourier transform has some limitations because if you want to probe the variations of the frequency content of the signal in time, then you get only a full time series representation when you take a Fourier transform. And also, there are some chirping waveforms that are more compact in the time frequency domain. And noise non-stationarities can happen. For example, the power spectral density of the noise can vary over some time scales. And having a representation that is flexible enough to represent this can be useful. So here, as an example, I have represented the discrete Fourier transform of a chirping signal. So this is the frequency domain data. But there is something else that you can do, is what is called the short-term Fourier transform, which is defined as, taking the Fourier transform of the data, but which has been pre-multiplied by the window that is centered around some time tau. And you can make this tau slide across the time series, right? And this is observing over, short duration segments here. So this is a short animation of what you may have when you take the short-term Fourier transform of a chirping signal, and in effect, when you apply this transform here in the discrete case, you get something like this, right? You have frequency on the y-axis and time on the x-axis, and there is a limitation to this short-term Fourier transform, which is that it has a fixed resolution. So yeah, here I forgot to mention that you can go back in time as well once you have taken the short-term Fourier transform. There is also an inverse operation. Okay, so this I will skip. This is about noise non-stationarity, and I will directly jump to the limitation of the short-term Fourier transform. So, you have a fixed resolution. So if you take a large window width, then you have a better frequency resolution, like here, but you have a lower time resolution. So there is a trade-off that you need to find between the two. And this is a bit restrictive, let's say. So that's why you will be manipulating what we call the Q transform, which is a short-term Fourier transform with a window width that depends on frequency. So, you know, the larger the frequency, the bigger the window will be. And this is helpful to have a kind of dynamic, you know, tiling of the time frequency space. So here, you see that the time of the size of the window is equal to Q divided by the frequency. So frequency is the central frequency of the time frequency bin, and Q is the quality factor that controls the trade-off between time and frequency resolution, right? So this means that if you have a high quality factor, then you have a high precision in frequency, and if you have a low quality factor, then you favor timing precision. So, okay, so I think I will have to quickly stop. I wanted to compare the different resolutions, so fixed grid for the short-term Fourier transform, dynamic grid here for the Q transform with longer. So yes, so this is just to illustrate the effect of this quality factor here, Q, where you see here, if you increase the quality factor, then you have, you know, a better frequency resolutions, but you have a smearing in time, which means that you have a less good time resolution. Okay, I need to conclude, so I will leave you with my conclusion and take question, and thank you for your attention.
Thank you very much, Quentin. It was a very interesting talk. In fact, this is the first year we do a signal processing talk. So you were the first one. I think you set the bar very high for the next years. Okay, before we take question in the amphitheater, there's a question online. So it's a question by Hadia Taleb. Could you explain leakage a little bit more?
Sure. So leakage is really due to this convolution that we have in the frequency domain. So actually, I can go back to the first slides. Maybe it describes it better. So let me go. Sorry, I'm browsing through my slides very quickly. Yeah. So, you know, you apply this time window, which is rectangular, for example, here, and this converts into a convolution in frequency. So that means that you will slide the Fourier transform of the window across the Fourier transform of your signal. And this will smear out the frequency content of S. And basically, you will convolve your data with, in the case of the rectangular window, this cardinal sine function in blue here. And especially because of the side lobes, you will, you know, pick up power of neighboring frequencies around the given frequency bin, right? So actually, if you have a high power peak in frequency and a low power peak right across it, then you may have power from the high power peak that leaks towards the low power peak, and that may hide it. So I don't know if it's clear like this. And so you have the same thing for the signals and for the noise. You have leakage for the noise as well.
I think that was clear. Thank you very much. I don't see any other question online. Is there a question in the amphitheater? Yep.
Hello.
Hi.
And we talk about the Nyquist theorem and the problem of aliasing in more details, because I see it in many contexts in signal processing.
Yeah. So basically, I mean, you see this representation here is the representation of the discrete time Fourier transform. Okay, so you have taken your data, you have sampled it every delta t, And this yields, and then you have taken the Fourier transform, okay? And you get this function here. This function is a function of frequency, and it's periodic. You know, every fs, if you take f plus fs here, you end up with the same thing. So you get, you know, replications of the same pattern, you know, every fs, okay? If, imagine that on this sketch here, the fs is smaller, so small then the second peak will overlap with the first one. Then you will have, you know, contamination in the frequency domain of the replication of the first peak, let's say. And that's why you need this fs to be larger than, you know, half of b here. Sorry, two times b here, because you want these two peaks to be sufficiently far apart so that there is no contamination. Yeah.
Is it fine? Yeah. Perfect. Any other question? Yep.
Could you go back to the Q transform? It was really too quick for me.
Oh yeah.
Yes, please.
I was quick. I'm sorry about the Q transform because I spent too much time on the first slides. So let me go back to the Q transform. Yeah. No. Okay, this. Sorry about this. Yeah. Basically, the Q transform is the same as the short-term Fourier transform, let's say. But now you adapt the window size with frequency. So the window is not only depending on time, right? But it also depends on frequency. And you want, if you're probing low frequency, you want, you know, long windows.
How would you adapt it? Is it proportional? In which way? And why is that? I mean,
okay. Yeah, I mean, in the case of Q transform, sometimes you will have, you know, logarithmically frequency tiling. Usually it's used in sound applications. But here, yes, here it's the relationship between the observation time and the frequency is inversely proportional, right? I guess you could pick a different choice. And this is actually going into what we call, you know, varying Q transform. But you could choose a different relationship here. Yes, indeed.
Okay, but is it optimal in any sense?
So the optimality depends on the signal you're looking for, right? Because actually it depends on the how fast the signal is evolving in frequency in time. Sorry. So for example, here, you know, you need to match this Q here, the quality factor, to be you know, at a given frequency, f divided by sigma f, so the bandwidth. That means that it should match the number of cycles the signal stays in this band, right? And so, for example, if you have a chirping signal, you could tune your Q based on the derivative of the frequency, for example. And this will be better for this purpose.
It reminds me of wavelet transforms.
Yes, indeed. I mean, I didn't talk about them, but another way of doing time frequency analysis is to do wavelet transforms, which are, you know, wavelet atoms that are usually quite concentrated in time. So, which is sometimes more convenient to do burst analysis, for example. And they're actually more flexible in the sense that you under certain conditions, you can build orthogonal, you know, basis, and also you have this advantage over the short-term Fourier transform, it's not a fixed resolution. You have also better resolution in time when you increase frequency. It's the same. Usually there are these dyadic wavelet transform where you multiply the resolution by the time resolution by 2 when you go in frequency. Yeah.
Thank you very much. That was a very interesting discussion. In fact, the Q transform is an important tool for the workshop. You will have in the tutorial, we'll have several Q transform to ensure. So keep in mind what we just talked about. Thank you.
Thanks.